In this outcome, we follow the whole journey of a statistical investigation, from framing a research question right through to a valid conclusion. Along the way, we'll look at sampling, processing data, and interpreting what it all means. It helps to see the whole process as a cycle. First, you ask a clear question and form a hypothesis. Then you plan and collect an appropriate sample of data. Next comes processing, tabulating, displaying, and summarizing what you've gathered. After that, you interpret it, drawing conclusions that actually answer your question. And finally, you evaluate the limitations and refine your approach for next time. Some foundational terms first. The population is the entire group you want to draw conclusions about. A sample is a smaller selection taken from that population. The sampling frame is a list of all the members of the population. A census is data collected from every single member. And bias is a systematic error that makes a sample unrepresentative. Let's weigh up a census against a sample. A census surveys everyone, so it's accurate, but it tends to be costly and slow. A sample surveys just a part of the population, which is quicker, cheaper, and usually far more practical. We then use that sample to estimate facts about the whole population. And the key is that a good sample is representative. The larger and fairer it is, the more reliable your estimate. So what makes a sample appropriate? It should be relevant, drawn from the correct target population. It should be representative, reflecting the makeup of that population. It needs to be large enough to iron out the effects of chance. It should be free from obvious bias in how members are picked. And realistically, it has to be practical to collect within your time and cost limits. Data comes in two broad types. Primary data is collected firsthand by the researcher through surveys, experiments, or observations, so it's specific to your question and up to date, though it can be time-consuming and expensive. Secondary data is already collected by someone else, things like census reports or official tables, which makes it fast and cheap to obtain, but it may be dated or not quite fit your particular question. There are three main sampling methods to know. Random sampling gives every member an equal chance of selection. Systematic sampling picks every KTH member from an ordered list. And stratified sampling splits the population into groups and samples each in proportion. Each one aims for a fair, representative sample, and the method you choose has a real bearing on how much bias creeps in. Let's take simple random sampling first. You number every member of the sampling frame, then use random numbers to decide who's included, so every member has an equal, independent chance of selection. Its great strength is that the selection is unbiased and easy to justify. The catch is that you need a complete list to start with, and by pure chance, it can sometimes miss smaller subgroups. Here's one in practice. A college has 200 learners numbered 001 to 200, and we use the random digits 137, 052, 194, 088, 137 to pick 4. Reading them in blocks of 3, we keep any value from 1 to 200 and discard the rest and any repeats. So 137, 52, 194, and 88 are all valid. That's our 4. And the second one, 37, is a repeat, so we simply ignore it. Systematic sampling works a little differently. You order the population and then choose every kth member, where the interval k is the population size divided by the sample size. You kick things off with a random start somewhere between 1 and k. It's quick and it spreads the sample evenly across the list. The one danger is that if there's a hidden repeating pattern in the list, it can line up with your interval and distort the results. Let's find an interval. A factory makes 1,500 items a shift, and an inspector wants a systematic sample of 60. The interval K is the population over the sample, 1,500 divided by 60, which is 25. You then pick a random start between 1 and 25, say 7, and select item 7, then 32, then 57, then 82, adding 25 each time until you've got all 60. Stratified sampling is about fairness across groups. You divide the population into strata, groups that genuinely differ from one another, and then sample each stratum in proportion to its size. The number you take from a group is its size divided by the population, times the overall sample size. Its strength is that it guarantees every group is fairly represented. The requirement is that you must know each group's size in advance. Let's work one through. A department has 120 Year 1, 90 Year 2, and 90 Year 3 learners, 300 in total, and we want a proportional stratified sample of 40. The sampling fraction is 40 over 300, which is 2/15, about 0.13. So Year 1 gives 120 times 2/15, which is 16. Year 2 gives 90 times 2/15, which is 12. And Year 3 the same, 12. 16 plus 12 plus 12 is 40, so it checks out. Bias is what makes samples mislead, and it wears several disguises. Selection bias is when some members can never be chosen in the first place. Non-response bias is when certain people simply fail to reply. Convenience sampling means only asking whoever's easiest to reach, and leading questions use wording that nudges people towards a particular answer. Any of these makes a sample unrepresentative and leaves your conclusions unsafe. Let's pause and check. Why might a survey taken outside a gym overstate how much people exercise? If a list of 800 names needs a systematic sample of 50, what's the interval K? And can you name one strength and one weakness of stratified sampling? Have a think. Before collecting data, it helps to form a hypothesis, a clear, testable statement or claim. A good one predicts a relationship or a difference you can investigate. For instance, learners who revise score higher in tests. The crucial thing is that it's specific enough to test with data. Once you've got it, you design your sample to gather exactly the evidence you need to check it. Once the data's in, we process it, and good tables and diagrams do a lot of the heavy lifting. Tally and frequency tables organize the raw numbers. Bar charts compare categories, while pie charts show proportions. Histograms display grouped continuous data, and line graphs show change over time. A well-chosen diagram will reveal patterns that a raw list of figures keeps hidden. Alongside diagrams, we summarize with a few key statistics. Averages locate the center of the data. That's the mean, median, and mode. The mean is the sum of x divided by n. The median is the middle value once the data's in order. The mode is the most frequent value, and the range, highest minus lowest, gives a simple measure of the spread. Let's lock those definitions in. The mean is the sum of the values divided by how many there are, the sum of x over n. The median is the middle value once the data's placed in order. The mode is the value occurring most often. The range is the highest value minus the lowest, a measure of spread. And frequency is simply how many times a particular value occurs. Let's compute some. 7 learners scored 12, 15, 15, 18, 20, 22, and 25. They add to 127, so the mean is 127 over 7, roughly 18.14. Ordered, the middle, fourth, value is 18, so that's the median. 15 appears twice, more than anything else, so it's the mode. And the range is 25 minus 12, which is 13. Here's a mean from a frequency table. Goals per match are 0 on 3 occasions, 1 on 5, 2 on 4, and 3 on 2. Multiplying each value by its frequency gives 0, 5, 8, and 6, which total 19 goals. The number of matches is 3 plus 5 plus 4 plus 2, that's 14. So the mean is the sum of fx over the sum of f. 19 divided by 14, about 1.36 goals per match. Interpreting results is where the investigation earns its keep. You compare what you found back against your original hypothesis, asking whether the evidence supports or contradicts the claim. Use your averages and spread to describe what you saw and state your conclusions in plain language, firmly tied to the data. Above all, be careful not to claim more than the sample can genuinely show. Let's draw a conclusion. Group A, who revised, averaged 72%, while Group B, who didn't, averaged 58%, with 20 learners in each. The difference is 14 percentage points in A's favor, and that direction does support the hypothesis that revising helps. But we should note, it's an association, not proof of cause. Other factors like prior ability or attendance might also differ between the groups. So the evidence supports the claim without proving revision alone caused the gap. It's worth being honest about limitations. Small samples give less reliable conclusions. Any bias in the sampling weakens whatever claim you make. Correlation, remember, doesn't prove causation. And your results really only apply to the population you actually sampled. So always state your limitations right alongside your conclusion. It's a mark of good statistical work, not a weakness. Let's contrast a weak conclusion with a strong one. A weak, overclaiming conclusion might be, this proves everyone prefers brand X, based on 10 friends asked at home, ignoring both bias and the tiny sample. A strong, measured conclusion would say, in our sample of 262% preferred X, drawn fairly across age groups, and it states its limits, one town, one time period. The second is far more defensible. Let's check your understanding. Can you find the median of 4, 7, 9, 11, and 15? Why should a conclusion always mention the size of the sample? And can you explain why correlation does not prove causation matters so much here? Give those a moment's thought.